Sorry, there were some technical difficulties. I think my screen got hanged. So let me again repeat the process for you. So in this lecture, we are going to discuss about collision. So let me share my screen with you people. Uh, Share. Okay. Close this. Okay. So here, this is about collision. So the process of collision begins uh, when two moving bodies, say one body is like this of mass m1, and let's say another body is of mass m2, and they collide with each other. Let's say their initial velocities are u1 and u2. So during the time of collision, they will come in contact with each other for a very small duration. Okay, so in that very small duration, they will impart impulsive forces over each other. Okay, so let's say this is some J12, that is impulsive force exerted by body 2 on body 1, and similarly body 1 will be exerting force on body 2. So let's say J21. Okay, so since this impulsive force act on each body in equal and opposite direction, okay, that will cause the change in momentum of these colliding bodies. So after the collision, their velocities will become, say, v1 and v2 uh, respectively. Okay, so the condition after collision can be predicted using principle of conservation of linear momentum. So conservation of linear momentum we will be able to apply on this system, okay, when we can make sure that during the collision there is no external impulsive force acting on the system. Then we will be able to write this equation of conservation of linear momentum, and that will be simply the linear momentum of the system just before the collision, that is m1 u1 plus m2 u2, and that will be equal to linear momentum in the system just after collision, that would be m1 v1 plus m2 v2. Okay, this equation we can apply along the direction in which we can make sure that there is no impulsive forces acting during the collision. This equation is nothing but another way of writing the impulse equation. Let's say, for example, here in this case, during the collision, equal and opposite impulsive forces are acting on it. So we can, this is very similar to like J12 would be nothing but minus of J21. So this is the equation we would be using for the collision. Okay, so another thing here I want to discuss is about something called line of impact. It is line of impact. As the name suggests that during the collision, the colliding bodies are exerting impulsive forces over each other, and the direction of that impulsive force will be known as line of impact. Like for example, let me show it illustratively. Like for example, this is the body and this is the body and this is the moment when they are in contact with each other. Okay, so the common normal at the point of contact will be nothing but line of impact. And here in this case, since we have taken both these colliding bodies as a spherical, so that would be the line joining their center. So this here is nothing but line of impact. Another example we can take, let's say for example, there is a plane surface and a sphere is colliding with it. Okay, so here this is the point of contact during the collision. Okay, and the common normal at the point of contact will be this. So this again would be passing through the center of a sphere, and here in this case this would be line of impact. So based on line of impact, collision can be divided into two categories, two broad categories we can say. That one type of collision is known as head-on collision, and the another one is known as oblique collision. The difference is, let me describe. Let's say, for example, there are two colliding bodies, and obviously this here would be the line of impact. So if the velocity of the colliding bodies before or after the collision is not along the line of impact, so here we are talking about head-on collision. So we can say, so velocities here would be along the line of impact. Okay, so the velocities has to be along the line of impact, say v1 v2. So velocities has to be along line of impact in order for the collision to be categorized as head-on collision. And if it is not along line of impact, for example, this is line of impact and the velocity of colliding body is something like this. Okay, so this would be the example of oblique collision. We will try to discuss both type of collision separately. Okay, before that, okay, let's try to discuss one more important aspect of collision, and that is known as elastic and inelastic collision. So I already said that when two bodies collide, they come in contact with each other for a very small interval of time. And during that interval, impulsive forces, equal and opposite impulsive forces, act over each other. So this situation, let's try to figure out. Let's say, for example, two colliding bodies are there. Okay, and they have come in contact with each other. Let's say its velocity was u1 and the velocity of this was u2 before collision. So when they collide, basically they will try to compress each other. They would be compressing each other first. Okay, and the shape of the both the bodies will be deformed a little bit. Let's say, for example, let's draw this diagram, something like that. Okay, so you can see that the body one m1 as well as m2 both has got deformed. Okay, so deformation means here the kinetic energy of the body, some a fraction of kinetic energy of the body will be converting into the deformation energy, or you can say elastic potential energy. Okay, so from here to here there would be like kinetic energy will be converting into elastic potential energy, and there would be see, all the body has some elastic property. Elastic property means like if the body is deformed and when the deforming force is removed, okay, the bodies tend to regain its shape, and that nature of the body is known as elastic nature. And if the body get deformed permanently, this nature would be inelastic nature. So up to a limit, all the bodies will try to regain its shape, and they will reform to some extent, and after the collision they will continue to move with some velocities v1 and v2. So this is what would be happening. So from here, like from this position to this position, kinetic energy will be changing into potential energy over here, and here again during the reformation, this is the process of deformation, and this is the process of reformation, you can say. So during the process of reformation, the deforming elastic potential energy will again be getting converted into kinetic energy of the colliding bodies over here. And also we must say, like from here to here, let's say this is the state of maximum deformation. Let's say middle one is the state of maximum deformation. So when the deformation is maximum, the loss in kinetic energy would be maximum. Like you can say, like the kinetic energy we know can be written as, in the previous class we saw, that can be written as half time total mass of the system, that is m1 plus m2, times velocity of center of mass square plus half times mu v relative square. So during the deformation, maximum deformation will be when like V relative becomes zero. So here in this case, you can say in this case V relative between the colliding bodies is equal to zero. That means the velocity of this body, the combined body, both will be moving with same velocity, and this would be VCOM, and the value of VCOM we already know. So that is M1 U1 plus M2 U2 divided by M1 plus M2, we can say. Okay, and during the reformation, this again will develop some relative motion between them because they are reforming over here. Okay, so if the reformation is not complete, let's say the colliding bodies have not regained their shape completely. So what we can say over here, like relative velocity before the collision or initial will be greater than that of relative velocity after the collision over here, that we can say, because whatever energy was converted into potential energy, the same potential energy is not converted into kinetic energy of the colliding bodies after the collision. So here this term, let's use a mod sign over here. So here this term enables us to define one more physical quantity that is known as coefficient of restitution. Coefficient of restitution, and that would be defined as E is equal to velocity, relative velocity of the colliding bodies after the collision divided by relative velocity of the colliding bodies before collision. In other words, we can write the same expression, that would be velocity of separation, that is after the collision, upon velocity of approach before the collision. So this is how one more equation we can derive. So obviously, let's say this is initial kinetic energy, and the final kinetic energy we can write similarly. So delta K here, the change in or loss in kinetic energy during collision, we can write. Okay, so see, when we write kinetic energy, that was half m1 plus m2 times v com square plus half mu v relative square. Since the velocity of center of mass is not going to change due to collision, so this term will remain unaltered. So before and after the collision, only this quantity will change. So initial kinetic energy becomes half m1 plus m2 v com square plus half mu v relative square initial, and similarly we can write an expression for final kinetic energy. So delta K would be simply, this term will get cancelled over here, and that would be nothing but half mu into v relative final square minus v relative initial square. So that would be the quantity over here, and we can see that v relative final is smaller than v relative initial, and that fraction is known as E. So this will turn out to be half mu v relative square, we can take common, and that would be E square minus 1, or you can say minus of half mu v relative square initial, you can use, and into 1 minus E square over here. So that basically the kinetic energy of the system would be decreasing. So on the basis of this, the collision can be further divided into two broad categories, and one is known as uh, elastic collision, and the another one is known as inelastic collision. So elastic collision is basically when we have loss in kinetic energy is equal to 0, or in this case the coefficient of restitution will be equal to 1. So velocity of approach will be equal to velocity of separation, whereas during the inelastic collision, okay, delta k will be negative, e would be less than 1. That means velocity of approach would be greater than velocity of separation. So in this category over here, there is loss in kinetic energy, and there is a special kind of collision which you can term it as perfectly inelastic collision. And perfectly inelastic collision means the velocity of separation is equal to 0. Velocity of separation equal to 0 means relative velocity of the bodies after the collision will be 0. So they will not be separating with each other after the collision. That will be, they will be moving with same velocity, common velocity, and that velocity will be equal to final velocity will be same as velocity of center of mass, or in that case the loss in kinetic energy would be maximum, and that would be simply equal to half mu v relative initial square, okay, or you can say half mu velocity of approach square. In all this discussion, it is clear, since we discussed in the previous class also, that mu here is nothing but m1 by m2 divided by m1 plus m2, which is also known as reduced mass. So here, when we are through with all these discussion of the types of collision based on line of impact, that is um, head-on and oblique collision, and the categorization of collision on the base of energy, that is elastic and inelastic collision. So now we are ready to discuss um, some problems over here. So here let's say a general case scenario, let's discuss. So we have already learned, say for example, two colliding bodies are there. So just before the collision, their velocities are in this direction u1 and u2, and after the collision the velocities are v1 and v2 over here. So that is M1 and M2. So if we know the condition before the collision, we must be able to find out the velocities after the collision, knowing the nature of collision over here. So first equation we are going to get from the conservation of linear momentum. So that is going to be M1 U1 plus M2 U2. It will be equal to M1 V1 plus M2 V2. And the another equation will be for coefficient of restitution, that is velocity of approach, velocity of separation divided by velocity of approach is equal to E. So here velocity of separation would be v2 minus v1, and velocity of approach would be u1 minus u2, and that will be equal to coefficient of restitution. So this is equation number 1, and this is equation number 2. We have two unknowns over here and two equation we have got, so we can definitely solve for v1 and v2. A few special cases which interests us. Okay, like first special case, if the collision is perfectly elastic and the mass of the colliding bodies are equal, so in that case the velocity of colliding body after the collision that results out to v1 would be equal to u2 and v2 would be equal to u1. That means after the collision the velocities are exchanged. Let me take one simple example. There are two bodies m. So before the collision, let's say this is moving with 5 meter per second and this is moving with 2 meters per second. So after the collision, this body will begin to move with 2 meter per second, and this body will begin to move with 5 meter per second. Over here you can see, because the mass of colliding bodies are equal. You can derive the result using these two equations, taking E is equal to 1 and M1 is equal to M2. Another case which interests us, another special case which interests us is when mass of one of the colliding body is very large in comparison to another. So let's say if m1 is much greater than m2, so it is very easy for us to predict the velocity of the heavier body just after the collision. Okay, and v1 would be approximately equal to u1. But I mean to say over here, due to collision, the velocity of the larger colliding body will remain unaffected due to the collision, because the collision, the other colliding body varies, is very small, and the velocity v2 definitely you can find out using the coefficient of restitution equation. So these were two special cases which particularly interests us. Okay, so now let's move on to some problem over here. So let me open another file for you. So let's talk about some examples of head-on collision. So this is one example of head-on collision I have taken, and here you can see one small ball over a large ball. Okay, and this is a very specific problem, very interesting problem. And a small ball over a large ball is known as super ball. Somehow it is known as super ball. You will very soon know why is that. So now look into the situation. So you can, let's read the description of this question. That is, a small ball of mass m is held above another ball of mass capital M with a little gap between them. There is a little gap between them, although it looks like they are in contact. Let's say there is a little gap between them, and they have been released from a height h. This height h is given. So how high will the smaller ball rise after collision? And we have to assume the collision to be perfectly elastic, and a capital M is much greater than a small m over here. So let's try to solve this question. So when the collision will happen, let's say firstly this larger ball will collide with the ground over here. Let's say just before the collision, this velocity of the collision would be v. Obviously we can find out the value of v, that would be root 2gh. So this collision is perfectly elastic from the ground, since coefficient of restitution is equal to 1. This would be rebounding with same velocity v over here, and at that instant this will be moving with same velocity, same speed in downward direction. That would be v as well. So let's say this is m and this is capital M over here. Okay, so this is the scenario over here. So this is the condition before the collision. So now see, here uh, when this ball rebounds, it is now going to collide with the smaller ball. Smaller ball is coming downward with velocity v, and the larger ball is going upward with velocity v. Acha, in this situation, we can see that the gravity is acting during the collision. So can we apply principle of conservation of linear momentum on this situation? Definitely we can. But because because even if the gravity is acting, gravity is not impulsive force. Gravity is a finite magnitude force, okay, which will not be changing the linear momentum of the system during the very small time interval of collision, because gravity is a finite magnitude force and time interval of collision is very small, tending to 0. So the gravity will not in fact be responsible for any significant change in the linear momentum of the whole system. So we can definitely apply principle of conservation of linear momentum. So just after the collision, the conditions would be, see, the larger ball, just now we have seen a special case between the collision between, for the collision between one very capital M greater than, much greater than small m. So after the collision, what we will be having, the velocity of this thing would still be very near to v only. And now see, before the collision, velocity of approach is 2v. So after the collision, velocity of separation is also going to be 2v. So this smaller body will be moving with 3v velocity. V plus 2v, that would be 3v velocity it would be moving. So the final velocity, since is 3v, okay, the height, the maximum height reached by this would be like, since v square, h maximum height would be directly proportional to v square. So the maximum height reached by the smaller ball will be 9h. Okay, 9 times the initial height from which it has been dropped. So the idea here is why it is known as super ball, because since we have dropped it from h height and it is rebounding till 9h height, so that is why we use this fascinating term, that is super ball. Okay, ball over ball is a super ball. So this is one case I wanted to discuss with you people. So now let's take some example. Let's talk about little bit about oblique collision over here. So say oblique collision. So let us discuss some theory about oblique collision. Okay, as we have already discussed, when the collision is oblique, okay, this is line of impact, which is the line joining their centers. Let's say the mass of this body is m1, the mass of this body is m2. So uh, this collision will be oblique when we can say that the velocities of colliding bodies necessarily is not along the line of impact. Say this is v1 and say this is v2, or u1 u2, better say u1 and u2. So let's say this angle is theta 1 and this angle is theta 2. So this is the condition before the collision. So we want to find out the condition after the collision. So let me use some other color pen over here. So let's draw over here. So condition after the collision, we can find out. Okay, so the idea to solve this problem is, say condition after the collision, this is moving with some velocity v1 and this is moving with some velocity, uh, let's say, let's take opposite direction over here. Let's say this moves with velocity v1 and this moves with some velocity v2, and say this angle is phi 1 and this angle is phi 2. So how are we going to get the condition just after the collision? So that is very simple. Two equations we will be writing here. So see, first equation, the thing is we will be resolving the velocities along two mutually perpendicular direction, and that will be one along line of impact and another would be perpendicular to line of impact. So let's resolve. So this u1, this component would be u1 cos theta 1 and this component would be u1 sine theta 1, and here before the collision this component would be u2 cos theta 2 and this component would be u2 sine theta 2. So this is the condition before collision, and similarly condition after collision we can say this would be v1 cos phi 1 and this would be v1 sine phi 1, and similarly we can write for this, that would be v2 cos phi 2 and that would be v2 sine phi 2. Okay, so one equation we must write over here, that see line the impulsive force on the colliding bodies is going to act only along the line of impact. So linear momentum of the colliding bodies will not change in a direction perpendicular to line of impact. So what we can say that this quantity, the perpendicular component, okay, will remain unaltered. So what we can say is u1 sine theta 1 will be equal to v1 sine phi 1, and similarly we can say the same thing about the body 2, means this quantity and this quantity are going to be same. So you can say u2 sine theta 2 is equal to v2 sine phi 2. So these two equations, the perpendicular components of velocity after the collision, it is very easy to get. And now we are required to find out the parallel components of velocity. And to find out the parallel component of velocity, we have to do the same thing as we did in case of head-on collision. That is, we will be applying principle of conservation of linear momentum. So let's take this as positive direction. So what you can say, that would be m1 u1 cos theta 1 minus m2 u2 cos theta 2, that is the linear momentum of the system just before the collision along the line of impact, and that will be equal to m2 v2 cos phi 2 minus m1 v1 cos phi 1 over here. That is conservation of linear momentum. And another equation we require will come from the equation of coefficient of restitution, and here we will be writing the coefficient of restitution only along the line of impact, because relative velocity is going to change only along the line of impact because the perpendicular component does not changes. So here velocity of separation definitely is v1 cos phi 1 plus v2 cos phi 2, and velocity of approach is nothing but u1 cos theta 1 plus u2 cos theta 2, and that will be equal to 1. So that is for oblique collision. So let's try to find solve a few questions over here. This is a question we can solve. That is two balls we are having, and let's say the mass here is m1 and the mass here is m2. So a moving sphere A of mass m1 experiences a perfectly elastic collision with a stationary sphere of mass m2 as shown. So this is moving with velocity u, and a sphere B is stationary just before the collision. At the instant of collision, the velocity vector of A makes an angle 30 degree with the line joining the center of A and B as shown in the figure. And after collision, spheres fly apart symmetrically relative to the initial motion direction of a sphere A with an angle of divergence 60 degree. Okay, so what does this statement means really? Okay, so let's try to find out the condition after the collision. So condition after the collision, it is saying that spheres fly apart symmetrically relative to the initial motion direction of sphere A. So this was the initial motion direction of sphere A, and the spheres fly apart with angle of divergence 60 degree. So see, on body B, the impulsive force is going to act on this direction. So its velocity will change in this direction only. So the velocity of M2 would be in this direction. Say that is V2 after the collision. And obviously this angle is given to us as 30 degree, and the another body is flying symmetrically with respect to this line. So this would be the line, and the body M1 will be flying in this direction with some velocity V1. So obviously this angle is going to be 30 degree, as we can see that the angle of divergence is 30 plus 30, that will be equal to 60 degree. Okay, so here now what we are intending to do is we are to resolve the motion in two mutually perpendicular components over here. So we can see that when we will be resolving this, Okay, so this will be this component here would be u cos 30 degree. So that would be root 3 by 2u, and this component is going to be u sine 30 degree, that is u by 2 over here. So this velocity, although this diagram is not very good, so two components we can resolve over here. Let me draw another diagram because this angle does not seem to be equal to 90 degree. So basically, let's draw another diagram. So this is V2, and this is some V1, and this is a 60-degree angle over here. So we have to resolve this V1 over here. So let me use some other color pen. So this is going to be V1 by 2, and this is going to be root 3 by 2 of V1. So you can see that this component and this component are going to be same. So one equation would be nothing but u by 2 is equal to root 3 by 2 V1, and another equation we can have from coefficient of restitution, because the collision is perfectly elastic. E will be equal to 1, means velocity of separation will be equal to velocity of approach. So velocity of separation is v2 minus v1 by 2, and that will be equal to velocity of approach, which is equal to root 3 by 2u. So that is equation number 1, and that is equation number 2. Another equation here we can write is for principle of conservation of linear momentum. So a linear momentum of the system just before collision would be m1 times root 3 by 2 into u along the line of impact we are writing, and that will be equal to m1 v1 by 2 plus m2 v2. So solving these three equations very easily, since we are required to find out m1 is equal to km2. So solving these three equations, we will be getting m1 is equal to 2m2. That means k is equal to 2 over here. So this is one question for oblique collision over here. And now let's look into one other problem of oblique collision. So this is a problem over here that is very regular problem. See, the problem description is a ball of mass m is equal to 1 kg over here is falling vertically with a speed of v naught is equal to 2 meter per second. When it hits a smooth inclined face of a wedge of mass capital M is equal to 2 kg. The wedge is on a smooth table. This table here is smooth, so that means it is free to move, and the coefficient of restitution is given to us as E is equal to half. So we have to find out the velocity of wedge after collision. So one must realize the condition before the collision and condition after the collision. So just like I said, so in case of oblique collision, it is always beneficial for us to resolve the velocity in two mutually perpendicular direction, and one is along the line of impact and another parallel to line of impact. So this angle here is 30 degree. So this component would be v naught cos 30 degree, that would be root 3 by 2 v naught, and this component here is going to be v naught sine 30 degrees, so that is v naught by 2. So this is the condition before the collision, and the condition after the collision we have to find out. So now this wedge is constrained to move only along the horizontal direction. So due to the collision, it would be moving somewhere in this direction. So that is, say, v2, and after the collision, this would be moving, this component of velocity will not be changing. So this component is still going to v naught by 2, and let's say this component will change. Okay, for let's say this value is some v1 over here. Okay, so we are required to find out v2. In this question, we have two unknowns, this v1 and v2. So we are required to write two equations involving v1 and v2. So how are we going to write that? So first equation we are going to write is for conservation of linear momentum on this system. So during the collision, we can see that this wedge is constrained to move only along the horizontal direction. So this impulsive, the normal in this case would be impulsive. So there is an impulsive, external impulsive force on this system in vertical direction. So we cannot conserve linear momentum along vertical direction. So but we can conserve the linear momentum of the system along the horizontal direction, and that is what we will be doing over here. So conservation of linear momentum equation we will be able to write along horizontal direction. So initial linear momentum of this particle or this ball over here just before the collision along the horizontal direction is 0. And after the collision, the linear momentum of this wedge we can write that is mv2, and the linear momentum of this body uh, here after the collision here is we can see like this angle here would be 30° over here, and this angle here would be 30° here as well. So the linear momentum of this particle of mass m would be minus m times, we can say that would be v naught by 2 cos 30°, so that is root 3 by 2 plus v1 sine 30°, that would be v1 by 2. So that is the equation for conservation of linear momentum. And coefficient of restitution equation we can write along the line of impact, So what would be the velocity of separation in this case? So velocity, in order to find out the velocity of separation, we need to resolve v2 also into mutually perpendicular direction. This is along the line of this is along the incline, and this is the line of impact. So this basically is 30°. So this is going to be v2 cos 30°. So v2 into root 3 by 2, and this component would be nothing but v2 by 2 over here. So velocity of separation, we can simply write, say that is v2 by 2 in this direction, and this body is flying with velocity v1. So that would be v1 plus v2 by 2. Okay, and that will be equal to e times, and e is given to us as 1 by 2 into velocity of approach. And velocity of approach is this, because before collision this wedge was stationary. So along the line of impact, the velocity here is root 3 by 2 v naught. So that is equation number 2. So solving these two equation values, small m, capital M, v naught, etc. are given to us. After solving, you are supposed to find out v2 is equal to 1 by root 3 meter per second. Okay. So this is one more example of oblique collision over here. So now let me discuss another important aspect, which is the involvement of impulsive force in the collision. So let's have some example of that nature. So let me open that file for you. So problem related to impulse. So for impulse, let's have some discussion of theory first. So impulse here is defined as, J is defined as like F dt, where F is the instantaneous force which acts during the collision and integral of that. And impulse momentum theorem simply says that that will be equal to change in linear momentum of the body over which the impulse is acting. That is known as impulse momentum theorem. Okay, and we will be using this would be simply m times, for example, v final minus v initial over here. So we will be using this equation in order to solve many problems. So let's discuss those problems over here. So this is one interesting problem. What we are having is a ball of mass m falls symmetrically on a set of 3 hemispheres. So this is a ball. Let me use some other color pen. This is a ball which is falling over 3 symmetrical hemispheres. So these are 3 hemisphere, top view of the hemisphere, and the side view, when we will be seeing it, will be looking like that. And it has been released from height h, and what else is given is mass of each hemisphere is m by 2. Mass of this is m by 2, m by 2, and one another sphere is like this, so m by 2, three hemispheres, and this sphere has mass as capital this m. So what we can say, neglect any rebounding of hemisphere here, and if spheres comes to rest after simultaneous collision with three hemisphere, the ratio of kinetic energy of sphere before collision and kinetic energy of any hemisphere after collision we have to find out. So here we are going to, in this situation, we are going to use impulse momentum theorem over here. So let's try to draw the diagram. So see, these three hemisphere are lying on the horizontal surface. So let's say the center of one hemisphere is A, the center of another hemisphere is B, and let's say center of another hemisphere is C. Okay, so and these three points will be forming an equilateral triangle on the ground, and its side will be equal to 2r, we can say. And just before the collision, uh, it will this sphere will fall symmetrically over it. So at that instant, the center of the sphere would be somewhere over here. Let's say the center would be at D. So if I join this point with another points A, B, C, so all the sides will be equal to 2r. This AD or BD or CD would be 2r. So this would be forming a regular tetrahedron at the instant. This is the geometry of the center of hemisphere and sphere just before the collision. And now you see, let's look at the geometry. So this would be the centroid over here. So basically this geometry I am drawing, so this is the vertical direction. Let's say this point is O. So when we join O with A, so this would be forming a right angle triangle over here. Okay, and if this angle is theta, so this side will tend to become 2r by root 3. So obviously sine theta, we can say that would be equal to 1 by root 3. So this is the geometry of case. So due to collision, like each of these three hemisphere will be exerting impulsive forces along these lines AD, BD and CD. So let's take one of the direction, and one of the hemisphere will be exerting some impulsive force, let's say J, on the sphere over here. So it will be having a vertically upward component. Okay, and this component we can say would be J cos theta. So this is the impulse exerted by one hemisphere on the sphere in the vertically upward direction. So since we are having three hemisphere, and so that would be 3j cos theta over there. So we are provided with the information that the sphere comes to rest after simultaneous collision. So its linear momentum will immediately become zero. So just before the collision, let's say its velocity was v naught, so it will become zero. So change in linear momentum will be simply equal to mv naught over here. So that is equation number 1. And similarly, when we will be applying impulse momentum theorem for any of the hemisphere, so this will be like let's say for A. So since it is exerting J impulse on D, equal and opposite impulse would be acting on A as well. So this would be J, and its linear momentum is changing along the horizontal direction. So this here angle is theta over here. So this component would be J sine theta. So J sine theta. And let's say after collision, this is moving with some velocity v dash. So J sine theta will be equal to change in linear momentum, and that would be m by 2 times v dash. So that is equation number 2. So just by dividing equation 2 with equation 1, what we will be getting is tan theta by 3 will be equal to v dash divided by 2 V naught over here. So that gives us V naught by V dash will be equal to uh, uh, will be equal to 3 by 2 tan theta, and from this data of sine theta, when we will be substituting the value of tan theta, it will become say 3 by root 2 over here. So this would be the value of V by V naught. Okay, and we are required to find out the ratio of kinetic energy of the sphere before the collision. So that would be half m V naught square, and divided by the kinetic energy of any of the ball before after collision. So that would be half into m by 2 into v dash square. Since we know the value of v naught by v dash, we can substitute this over here, and this answer we are supposed to get as 9. So that is one problem over here. And one another interesting problem I want to discuss with you people, where we will be having impulsive normal in this case. See, so the situation which we are facing here is there is a ball of mass m hits a flat horizontal surface while traveling with velocity u. The angle of incidence is theta. This angle is theta, and coefficient of restitution is given to us as e. The only difference is the coefficient of friction also of this surface, and the ball is given to us as mu. Okay, so this surface is rough and having coefficient of friction as mu. So we are required to find the velocity of the ball after the impact over here. So again, let's resolve the velocities along line of impact and perpendicular to line of impact. So this angle here is theta. So this is going to be u cos theta, and this is going to be u sin theta. And after the collision, let's say it will be flying in this direction. So say this would be some Vx and this would be some Vy, and we are required to find out the value of Vx and Vy over here. So using impulse momentum theorem, using impulse momentum theorem, first of all, we can say impulse momentum theorem when we will be applying along. So what impulse would be acting on this body during the collision? So there would be impulsive normal over here, and impulsive. So when the normal is impulsive, the friction here will be impulsive as well. So that would be impulsive friction as well. So Jn, we can write Jn, we can write it as the change in linear momentum along the normal over here would be m times um, u cos theta plus Vy over here, and impulsive friction would be impulse momentum theorem along the horizontal direction. If we are applying, Jf will be equal to what we can say would be m times u sin theta minus Vx over here. So that is equation number 1, that is equation number 2. So since Jn is also Jn, you can say also equal to Jn will also be equal to integral of n dt, and Jf will also be equal to integral of f dt. So when we will be dividing this equation number 1 and 2, so what you will be getting is f by n. So equation number 2, that would be u sin theta minus Vx divided by sorry, u sin theta minus Vx, and that divided by u cos theta plus Vy, that will be giving us f by n, and that would be f by n would be nothing but mu over here. So this is one equation, let's say equation number 3, and another equation we will be having for coefficient of restitution. So velocity of separation, as we can see, is nothing but Vy, and velocity of approach is u cos theta. So Vy you can write it as EU cos theta. And when we will be substituting this value in equation number 3, we are supposed to get Vx is equal to u sine theta minus mu times u cos theta into 1 plus e. So this was one example where we had impulsive friction as well. So in the next class, we would be discussing more problems of collision involving impulsive forces, and we will look into one very important aspect, that is collision in center of mass field. And here I'm going to end this session with this. Thank you very much for joining. Thank you.